Hi, I'm Dr. TJ again, and I'm very excited to introduce our second speaker, who is Kindall Brown. Kindall has been working with me for a year. She comes from a great experience before this in working in streams in order to understand their biodiversity and also their stream health. And so I'm very fortunate that she has decided to come to JSU in order to continue on that work and understand a bit about biodiversity in a creek that's not very far from us.
I will take it away from you. So I am doing my research and my thesis on the relationship between changing lake cover and macroinvertebrate diversity over 20 years in Choccolocco Creek, northeast Alabama. So there are a few ways that land development can impact our creek systems, such as deforestation. So rural land grading, integration of drainage systems, and removal of soil, this can all lead to flooding, which can definitely add in nutrient loading and chemical pollutants, which leads to poor water quality and low species diversity, which is basically an overview of what I'm going to be talking about today. So specifically, my research is on Choccolocco Creek. Choccolocco Creek, it has about 300,000 acres and runs 70 miles into the Coosa River drainage basin, making it one of the largest tributaries. And so it starts in the Talladega National Forest and it runs down into from Claiborne County into Calhoun and Clay counties. And our Site 1 is our headwater stream, which is our reference stream. So in 2000, a survey of benthic macroinvertebrate diversity was conducted, and it showed declines in biodiversity along the length of the stream. So these declines become more pronounced through time based on data collected from a repeated survey in 2011, and continued declines are expected. So there's a survey scheduled for 2022 and 2023, which is what I'm currently working on. So in these last two surveys, the documentation of land use was not given. So I did a detailed assessment of land use cover differences between 2000 to 2011 to 2019 using data made available by the National Land Use Land Cover Landsat imagery needed for all years. So as you can see, there is a distinct rural-urban gradient on our sites 2 and 3, and this correlates over here to where our sites run through. We have a legend that shows the land use differences in colors. And you can see that it's changing through the different years as it goes on, but I wanted to quantify that. And I wanted to see the percent differences in between land use changes. So this is what my data showed. From 2001 to 2019, our mixed forests decreased from 69% to 66%, and our developed open space increased from 11 to 14%. And most of this developed open space was high-intensity development. So I wanted to look at how that compared to the total organisms and total taxa from the previous surveys that were done. So in this graph right here, it shows that there have been significant declines in the total organisms from our sites 1, 2, 3, and 4. We kind of see site 5, it jumps up a lot in total organisms, but we have the same pattern going here. But if you look at site 5 comparatively, the total taxa and species richness is very low when you're comparing to how many total organisms there are. So it's not always a great thing that there are an abundance of organisms when there's not great species richness within those organisms. Sites 3 and 4, there have been significant sedimentation and human impacts observed at these sites. And so that is another reason why these may have degraded significantly. And then our Site 1, our headwater site, it does show that there are less organisms in total taxa, but that is because it is a smaller stream system, and when you have smaller stream systems, you're obviously going to have less total taxa and total organisms. The universal ecological and physical responses of streams due to increased urbanization is referred to as the urban stream syndrome. This is changes in stream morphology, hydrology, chemistry, and biology. But our most problematic is altered channel geomorphology. So over here, we have a comparison of a natural and an urbanized stream channel. As you can see from the pictures above, and this describes below too, that there is very low groundwater recharge and very low evapotranspiration within the urbanized stream channel of this stream. And so the picture shows that the water does not get down into the soil, so we have reduced soil moisture retention, and that increases the environmental temperature as well. Our stream hydrology of an urbanized stream is very peaky, meaning that you can have flash floods, unpredicted high and low water tables, which is not great for biodiversity. And then the riparian vegetation and the channel form is degraded on our urbanized as well. And we'll get into more on how that can affect our biodiversity within the streams. The picture it's showing right here, our deepened water table and how sediment can run off. But I wanted to show a picture of what that would actually look like if you were in the field. So this is our unhealthy versus healthy geomorphology of a stream channel. To this side, we have increased sedimentation and this cut bank that just drops off without very much vegetation. This leads to channelization, which is deepening and widening of our streams, and that gets rid of our mesohabitats, our riffles, runs, and pools that are very important for our aquatic organisms. As you can see on this side, this is what a stream should look like. It has plenty of vegetation. We have riffles, we have pools, we have runs, and not a lot of bank runoff, so it gradually slopes down, and we have meandering as well. So I wanted to specifically look at how land use can affect macroinvertebrate diversity. That is a mouthful to say, so if I mess it up a bunch of times, I'm so sorry. Three of the major ways is altered flow regime, which is loss of mesohabitats I've stated before needed for survival. These are riffles, runs, and pools. So the change in stream velocity, depths, and substrates needed for spawning and food resources, they degrade with altered flow regime. And then we have the removal of our riparian zone. This leads to nutrient and sediment loading, leading to increased pollutants and less permeable stream beds. As fine sediment is input into our stream systems, it can get down in between our rocks on the bottom of the stream surface. And that makes it hard for aquatic benthic macroinvertebrates who live in those habitats and to be able to maneuver around between the rocks. And the colonization of success depends on dispersal abilities to suitable terrestrial habitats from larval to adult stages. So their larval stages are aquatic, and then their adult stages are terrestrial. So without the riparian zone, and if that's an unfamiliar word for you, it's a vegetated zone, they cannot colonize. They cannot colonize, I'm sorry. And then we have the disconnection of in-stream channels and networks. So this leads to loss of ability to populate and diversify the entire stream reach, the loss of movement for developing and traveling insects, and less species richness and populations within our aquatic habitats. So, why should we care about aquatic benthic macroinvertebrates? As Dr. TJ always points out, they're not big, cuddly, furry, cute animals. In my very unbiased opinion, I think they're pretty cute. But the impact that they have on our stream quality is very cute, soft, and cuddly. So this is why we should look at how they affect our stream systems and why we should care. So one of the main reasons, or the main concept of my research, is macroinvertebrates are used as bioindicators. They can be quantified. And so this table right here is a table that shows our tolerance values for different macroinvertebrates. 0 being the most intolerant of stress and pollution, and 10 being the most tolerant. So we can group these into 3 different groups, where our group 1 cannot tolerate pollution and they need cold, clean water to survive. And then we have our medium quality, which are still considered intolerant, but they can tolerate some pollutants in the water. And then we have our group 3, which they can tolerate pollutants in the water and poor water quality conditions. Going back to our Site 5, this could be a possibility of why there's so many organisms, but less taxa. So I took our data and I wanted to see what this looked like with our matrix and our biotic indicators. So this is our tolerance matrix of taxa 2000 versus 2001. And for our EPT taxa, these are our orders that are extremely intolerant. There are clean water species. They cannot tolerate any sort of pollution. And so we have our moderate and then our tolerant. And I compared each side from 2000 to 2011. And as you can see, it does go down by year and also by side. And so we lose a lot of our EPT taxa and we gain a lot more pollutant tolerant taxa. So I'm going to take those percentages and compare these. So sites 3 and 4 specifically, our tolerant taxa went from 35% to 72%. And site 3, our tolerant taxa went from 43 to 69%. Whereas our EPT taxa, or our intolerant taxa, it decreased from 46% to 28%, and site 3 from 40% to 28%. So we have a decrease in all of our sites except for site 5, which is kind of the anomaly there. But our EPT taxa still went down from 35% to 18%, and a lot of them became moderate from 50 to 37%. So EPT taxa and intolerant taxa decreases with decreasing water quality and provides a reliable indication of biological conditions at sites with human influence. And this goes along with our prediction of the river continuum concept, meaning that from the top of the river to the bottom of the river, biological and physical aspects are all integrated, which is definitely something to think about when you think about habitat restoration. You can't just do one without the other. Everything within that is integrated. So, in conclusion, our aquatic benthic macroinvertebrates are affected by physical, chemical, and biological conditions of the stream, and their sensitivity to pollution has been quantified. They can escape pollution due to their limited mobility. Therefore, benthic macroinvertebrates are a good indicator of localized conditions over a relatively long period of time. These long-term assessments of our watersheds are critical for determining biodiversity changes due to stream degradation, and this can allow for timely action to prevent total degradation. This helps us better understand how certain impacts can affect stream animals as well as recovery from such events, and plan site-specific restorative projects to help rebuild and maintain our impacts. And I will close with the comparison, which I thought was pretty perfect, that for macroinvertebrates to stream health has been compared to a thermometer as health for humans. And so these little guys are extremely important and we should protect them. Do we have any questions? Any questions? Yes, ma'am.
So I was trying to keep up with all your sites, but is it right that Site 5 has had some recovery and
Yes.
improvement, and do you know why that was?
So there have been some restorative projects going on in Site 5, and that's all I really know. I can't wait to see my data that comes out to really see how much of the restorative project has helped. So I know that you are all on the edge of your seats wondering what taxa is going to be there when I do my thesis defense. But that will be until the end of the year.
Where is site five?
Site 5 is, it's all the way down here where, around Lincoln.
I can't wait to hear this.
I can't wait to get my. Yes, Dr. Raver.
Is site 5, is that in the sites that Monsanto, is that the same watershed where Monsanto's stuff is?
Is it? You're saying it's.
Okay,
It's
so
down.
site 5 is in where recovery, EPA bought a lot of land along that area, and they sort of prevented people from going along the riparian zone we're talking
Right,
about.
and they are building like a little park and stuff there and different trails and stuff as well. And it does keep you off of the riparian zone. And it does have a disconnected floodplain. And so I know that there are some projects going on to try to connect that floodplain in.
When you're looking at your NDVI and the land cover, land change, and you're thinking about the area, are you thinking local, or when you did your percent change, did you do it based on the entire farm?
So that's a good question. I did this based on this entire land use land cover. I'm going to, for my thesis, I'm gonna go back and put a buffer, and we're gonna see how that changes as it goes away from the stream. I know that sites 3 and 4 definitely runs through Oxford, where there's a ton of human impact and development, and so I would like to take this and make it smaller and look at our buffer zones there. But the main changes are along where our stream reach would be.
All right, if no more questions, let's thank our speaker again.